In this video, we're going to discuss something called an antiderivative, and we're also going to talk about what's called an indefinite integral. Now, this stuff is going to feel very unrelated to our last video involving area, but I promise it's all going to eventually come together, so just hang in there. So let's start with what the definition of an antiderivative is. A function f is an antiderivative of some other function, which I'll call little f, on an interval I, if the derivative of capital F is equal to little f for all x in our interval I. So that's not too bad. Basically, we're just saying an antiderivative is the opposite of a derivative. So instead of having a function and we need to find the derivative of the function, we're going to be given a derivative and we need to find what function did this derivative come from. So let's do an example. Let's just start with little f equals x squared. And we want to find an antiderivative of little f. Well, let's first just think about taking derivatives. When we take a derivative using the power rule, we know that the exponent decreases in size. Remember when we had x to the third, the derivative of x to the third would be 3x squared, so the exponent goes down by 1. This tells me that whatever I took a derivative of should have an exponent of 3, so it would become an exponent of 2 when I do the derivative. So let's just take a guess for an antiderivative. I know there's going to be an x to the third. The problem with that, though, is if I tried to double check by taking the derivative of this result, I get 3x squared, which is not what I wanted. I wanted x squared. So x to the third is not an antiderivative of x squared, but I can fix it so that it is. Over here, I see that I got my derivative was 3 times larger than I wanted it to be. So what happens if I divide by 3 over here? So is 1/3 x to the third an antiderivative of x squared? Well, let's check by taking the derivative and see if it checks out. If I take the derivative of this using the power rule, my 3 is going to come down and multiply onto the 1/3, canceling it out. And my new power is going to be 1 smaller, and I get x squared, which does in fact work. So f of x equals 1/3 x to the third is indeed an antiderivative of x squared. But is it the only antiderivative? The answer to that is no, it's not the only antiderivative. For example, what if I gave us capital F equals 1/3 x to the third minus 2. Well, let's take a derivative of this antiderivative to verify it works as well. If I take the derivative of this capital F, again, the 1/3 x to the third gets me x squared, and the derivative of the minus 2 is 0 because the derivative of a constant is 0. So this guy also worked as an antiderivative. Are there others? Of course there are. What if I wanted to be really obnoxious with that constant, and I said, well, how about 1/3 x to the third plus 100 pi squared? That's a really ugly constant, but 100 pi squared is still just a constant. So if I check this by taking the derivative, I still get just x squared because the derivative of that 100 pi squared is still 0. So now I have 3 different antiderivatives for the same function. And are there more out there? Yeah, there's actually infinitely many antiderivatives for that function x squared. And so we can write it in a generic way. If capital F is an antiderivative for little f, on some interval I, then the most general antiderivative of little f on the interval I is capital F plus c, where c is an arbitrary constant. So for the example we had just done, trying to find the antiderivative of x squared, we could now write the generic answer of 1/3 x to the third plus c, where c is any constant that I want. All right, so now we know there are infinitely many antiderivatives. So let's get some practice finding some antiderivatives. This ends up being really fun because we already know a lot of derivative rules, and now we have to try to start doing all of our derivatives backwards. So everything you've learned so far in Calc 1, we're now going to do it all backwards. Should be a lot of fun. Examples. Find the most general antiderivative of the following. And my first one is going to be f of x equals sine of x. So I want to find a function that when I take the derivative of it, I get sine of x as the derivative. Well, let's think for a second. We know that cosine, if I take the derivative of cosine, I get negative sine. So I'm going to need a cosine here so that I get a sine function, but it's going to have to be negative so that the derivative ends up being positive sine. And then I need my plus c to make it the most generic version of an antiderivative that I can. That one's not too bad. It's just a little tricky because we have to remember all the positive and negatives that we get with our trig functions. Make sure that we are doing it properly. So let's try another example. Part B. Part B, let's find the most general antiderivative of f of x equals x to the n power, where n is some number bigger than or equal to 0. Well, this one's kind of like what we already did with the x squared. We ended up getting the antiderivative by knowing that the power should end up being 1 larger. And then remember with that x squared, we ended up with x to the third in the antiderivative, but we had to divide by 3. So I'm going to try dividing by n plus 1 and add our constant. Let's double check that this indeed undoes our power rule from before. If I take the derivative of this result, the n plus 1 would come down, multiply, canceling out that denominator, and my new power would just be 1 smaller, so it'd be n. So this does work as the antiderivative. So to undo a power rule, our original power rule for differentiation, we brought the power down and multiplied, and then we subtracted 1 from the power. Doing that backwards, we're going to add 1 to the power and then divide by that new power. So let's try another one. What if I have f of x equals x to the negative third power? Well, let's try undoing the power rule like I just described. We can try adding 1 to the exponent, divide by that new exponent, and have our plus c. And let's simplify this answer so it looks a little better. That would be an x to the negative 2 over negative 2 plus c. Did this work when we reversed our power rule? Yes, it did. The derivative of x to the negative 2 over negative 2, negative 2 would come down, multiply, canceling out the denominator. New power would be 1 smaller, making it negative 3. Derivative of constant is 0. So it does check out. All right. So those ones aren't too bad. We had one trig function that we worked with. We had a couple power rules. Those aren't too bad. But of course, we can have more and more complicated functions that we have to find the antiderivative of. Let's do a more complicated problem. Find all functions g such that the derivative of g is equal to 4 sine of x plus, let me write this on a new line, I don't have enough room for it. G prime is 4 sine x plus 2x to the 5th minus square root of x over x. That's a pretty complicated derivative, and I have to find the antiderivative of this. Notice they're asking for functions that when I take the derivative, I get this result. So finding the antiderivative is exactly what I need to do. I would highly suggest that when you look at this term over here, we should probably split that into 2 fractions, make it a little easier to work with. And I also would rewrite the square root as x to the 1/2 power, just to make it easier on me. So that's where I'm going to start. Let's rewrite our derivative. I have 4 sine x plus 2x to the 5th over x minus x to the 1/2 over x. Now both of these fractions over here, we can simplify a little bit before we find the antiderivative. Simplifying those fractions, we get that the derivative looks like 4 sine x plus 2x to the 4th minus an x to the negative 1/2 power. And I got those just by subtracting the exponents. Now I'm ready to find the antiderivative of g prime, which would just be g. Well, let's start with that 4 sine x. Remember from earlier, the antiderivative of sine was negative cosine. Having that 4 in the front doesn't change things too much. It just means I'm going to have negative 4 cosine of x. Double check that before we go on. If I were to take the derivative of this, I would have negative 4 times the derivative of cosine, which is negative sine. So that'd be positive 4 sine, and I got that. These other two have power, so I get to try to do that backwards power rule. Add 1 to the exponent and divide by the new exponent. Add 1 to the exponent, divide by the new exponent. And don't forget your c. Well, that looks kind of ugly, having this dividing by 1/2. So I'm going to rewrite it in a way that looks a little better. I have negative 4 cosine x plus 2x to the 5th over 5 minus 2x to the 1/2 plus c. And I got it as a 2 being multiplied because dividing by a fraction is the same thing as multiplying by the reciprocal. So instead of dividing by 1/2, I multiplied by 2. And this gives me an expression saying every single function whose derivative was equal to that derivative I was given. Not too terrible, I hope. I happen to really enjoy doing antiderivatives, and I hope you end up really enjoying it too. So that is what an antiderivative is. But there is another notation that tells us to take an antiderivative, and it's something called an indefinite integral. So let's get this definition. The indefinite integral of f is the antiderivative of f. So what this looks like, this is our notation for the integral. Let me finish writing this down and I'll explain. All right, so this notation right here is the notation for an integral. This symbol here, it kind of looks like a capital S that's been stretched out. And really that comes from the fact that it actually is talking about a sum, but don't worry too much about that. We'll get into that in future videos. Right now, just think of this as a symbol telling you it's an integral. This dx also goes along with that symbol. You think of them as being matched up as a pair. This dx is actually a differential. We're going to get into that a little bit more. I know we talked about differentials earlier in the semester, but for now, you can just think of this as being paired up with this integral symbol telling you you need to find an antiderivative. So the integral of f of x with respect to x is equal to capital F plus c, where capital F is an antiderivative of little f. So this fancy notation here is just saying, hey, find an antiderivative. So for example, let's do the integral of x to the n. Where n is not equal to -1. So n is going to be any power except for -1. Well, then I can do that backwards power rule that we already learned. The integral of x to the n with respect to x, I add 1 to the exponent and divide by that new exponent and add my c. All right, that's not too bad. Now, why did I say n is not -1? Well, because if n were -1 and I use this formula here, I would have an x to the 0 divided by 0. And we're not allowed to divide by 0. So what would we do if we had this situation where we had n is -1? That's where it looks like this. The antiderivative of 1 over x. Any ideas? Try to think of a function that when you take the derivative of it, you get 1 over x. And I can't hear you at home right now, but I hope you're yelling out natural logarithms, because the derivative of natural log gives us that 1 over x. So we do get for our antiderivative the natural log, and it's of the absolute value of x plus c. Now, why do I have absolute values there? Well, because logarithms can only take inputs that are not negative. So I don't know what x is at this point. But to make sure that my natural log is well defined, I need to make sure that this guy does not have negative numbers being plugged into it. So I have to put absolute values around there to ensure that that x ends up being positive. All right, let's do one more antiderivative for now. How about the integral of 10x to the fourth minus 2 secant squared of x dx. Well, that one looks a little bit scary, but we don't have to worry too much. Just like with derivatives, having numbers multiplied in the front doesn't really matter that much for antiderivatives. Those numbers just get to stay. And adding and subtracting in between, we can just take the antiderivative of each piece and still be okay. So I'm going to use that power rule on this first guy. And on the second guy, I have to try to remember what trig function has a derivative equal to a secant squared. Well, let's take care of this power rule first. My 10 gets to stay. We add 1 to the exponent, divide by our new exponent, and I'll simplify it later. Now we're ready for that secant squared. My 2 is still going to be there with that minus sign. What function has a derivative equal to secant squared? And again, I know you're at home just shouting out, it has to be tangent, and that is correct. The antiderivative of secant squared is tangent, because the derivative of tangent is secant squared. And then am I missing anything else on this problem? Yes, I'm missing my plus c. We always have to have that constant at the end because this actually represents infinitely many answers, a family of functions, if you will. They're all the same type of function, they just differ by that constant at the end. And now let's just simplify the answer because it's not too bad to do. That 10 over 5 simplifies to 2. I get 2x to the 5th minus 2 tangent of x plus c as my integral or my antiderivative. Now, at this point, you might be wondering, well, how do you know if you did the answer correctly? And this is the great thing about our antiderivatives. We are so good at derivatives now from doing them all semester that if you want to check if your antiderivative is correct, just take the derivative of your answer. If the derivative of your answer equals the stuff you had here in the integral, you're good to go. So let's double check this real quick. The derivative of 2x to the 5th, 5 would come down and multiply, and I'd get 10x to the 4th. That matches right up there. And the derivative of the minus 2 tangent would be minus 2 times the derivative of tangent, which is secant squared. So I'd have minus 2 secant squared of x, which is right there. And the derivative of our constant is 0, which is why I don't have anything up there for that. This does check out. All right, let's see here. We need to do another example. I think probably just maybe 2 more examples for today. But rather than just saying find an antiderivative or find an indefinite integral, we're going to do something called a differential equation. Now, a differential equation is an equation that uses derivatives. So, an equation that involves the derivatives of a function is called a differential equation. Now, in this class, Calculus 1, We do a little bit of differential equations, but we don't do very, very complicated differential equations in this particular course. There are mathematicians out there who pretty much do nothing but differential equations or diffie-qs all the time. There are whole courses devoted to differential equations, and then whole entire research areas involving differential equations. We're only going to do the very basics in this particular course, but if you find it kind of fun, you might want to look into a differential equation course in your future. So let's do a differential equation problem. We have find f if f prime is equal to x times the square root of x, and f of 1 equals 2. So I'm given the derivative of the function, and I want the original function. So I'm going to have to find an antiderivative. This last little bit of info here, we get to use that info to find what our constant c is. But let's find the antiderivative first. To do that, I would rewrite my derivative. F prime is x times x to the 1/2, which that's the same thing as x to the 3/2 power. So now if I want to find the antiderivative of that, I get to use that backwards power rule. Add 1 to the exponent, so that would put me at 5/2, and divide by that new exponent. Dividing by 5/2 is the same thing as multiplying by 2/5, so I'm going to write it that way. And then add my constant. This would be the general antiderivative of that function, but now I can find my constant because I have more info. I have that f with 1 plugged into it should get me a result of 2. Let's plug that in. So plug in f of 1 equals 2, and that will get us 2 is equal to 2/5 times 1 to the 5/2 power plus c. Well, 1 to the 5/2 is still 1. So I have 2 equals 2/5 plus c. If I subtract that 2/5 to the other side, I get my constant is 8/5. So now that I have my constant, I'm ready to write my final answer to the problem. F of x is equal to 2/5 x to the 5/2 plus the c that we just found, 8/5. All right, so congratulations, you just solved your very first differential equation. Though it wasn't too bad, it was finding an antiderivative, plugging in some values to find the constant. If you do take differential equations courses in the future, you're going to need to get really good at antiderivatives and our integration that we're learning. Let's do one more example for this video. It's going to be a little bit longer of an example. Find f if the second derivative of f is 12x squared plus 6x minus 4, and f of 0 is 4, and f of 1 is 1. All right, so this one's only a little bit different because I was given a second derivative. So if I take an antiderivative of my second derivative, it's going to get me the first derivative of my function. That means I'm going to have to do 2 antiderivatives to get back to the original f. So here is my second derivative. 12x squared plus 6x minus 4. If I do an antiderivative, it will give me the first derivative of my function. And we get to do a lot of our backwards power rule on this one. I'm going to add 1 to my exponent and divide by my new exponent. This guy has an exponent of 1, so I'm going to add 1 to that exponent, divide by the new exponent. And now what about this minus 4? What has a derivative of just a constant? Well, I just need to put an x on there. The derivative of negative 4x is negative 4. And then don't forget your plus c at the very end. So that's my first derivative. I'm going to try to simplify it a little bit. My first derivative, when I simplify my fractions, is 4x to the third plus 3x squared minus 4x plus my constant. Now I'm going to do the antiderivative again to get me f. Doing another antiderivative, I have a power rule again, so I'm going to add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent. Now what do I do with that c? Well, that's just like what we had here with this minus 4. Antiderivative of a constant is that constant times x, because the derivative of a constant times x is just the constant. And now I need another constant added on. I'm not going to call it c this time because I already used c, so I'm going to use d over there. So that's what f looks like. Let's simplify those fractions a little bit to make it a little prettier. And we have f of x is equal to x to the fourth plus x to the third minus 2x squared plus cx plus d. But now I have to figure out what c and d are. But luckily, I was given 2 different pieces of information. So using the fact that f of 0 is equal to 4, let's see what we get. F of 0 equals 4, so that means I have 4 on this side, and I plug in zeros for all of the x's. And I get that 4 is equal to d. So now I have what d is. Let me rewrite what my function looks like. I have x to the fourth plus x to the third minus 2x squared plus cx plus my d, which is 4. So now I still have to figure out what c is. To figure out what c is, we just plug in the other bit of information we had. So using the fact that f of 1 is 1, we can figure out what c is. So I have 1 equals what I get when I plug a 1 in for all of my x's. So I get 1 equals, well, this is 1 plus 1 minus 2, so that goes away, and I just get c and 4. So that means c is equal to negative 3. So now I have what c is equal to, and I can write the final answer to this problem. I have f of x is x to the fourth plus x to the third minus 2x squared. And then I have my cx, so that's a minus 3x. And then plus my d, which was 4. And that is the final answer. So that was a slightly more complicated differential equation problem. but it still wasn't too terrible, I hope. So this was actually a lot of information in one video. We've learned what an antiderivative is. We've had a couple different examples, some with trig, some with the natural log, a lot with the power rule. And we've learned how to solve some differential equations using our antiderivatives. In the next video, we're going to learn one of my very favorite things of all of calculus. It's something called substitution for integrals, and it's so much fun. So I'm hoping you'll enjoy the next video. I'm really looking forward to making it. If you have questions, feel free to drop them down below, or if you're in my class currently, you may come to my office hours virtually or email me questions, and I'll answer your questions there as well. I will see you next time.